Okay. Okay, good. I will tell you, tell me that I am allowed to start. Captain will.
Yes.
Yes. Some place. I think that. It's fine. Yeah, please. Okay, so I welcome all the participants who are in this room and also the ones who are online. I see that there are a few of them. So welcome to everybody. Thank you. So I already gave some lectures on a similar topic in previous conferences, but I do not suppose that all of you attended my previous lectures, so I will make this one independently of the others. But nevertheless, I will start by reminding you what I said in the previous conferences. In 2018, I gave a report on the Landau-Ramanujan constant, and it was a joint work with Claude Levesque and Etienne Coubry. In 2019, I gave a lecture on the representation of integers by cyclotomic binary forms of large degree, and this was a joint work with Etienne Coubry. And now we have another joint paper with Etienne Coubry, which is submitted to Acta Arithmetica, and I will report on that. I did not give a talk in 2021. It was an online conference, but I attended all the lectures, but I did not speak.
It was dedicated to you.
This is why I did not give a lecture. And so I will start with some, to remind you, well, to tell you a few words about the talk which I gave in 2018. It was on the Landau-Ramanujan constant, and as it should, I will start with the work of Ramanujan. The Landau-Ramanujan constant is a number, it's a precise number, 0.764 and so on, which is related with the problem of writing an integer as a sum of two squares. And the question is to consider the number of integers n in Z, which are one between 1 and n, which has the form which are sum of two squares. So n equal x squared plus y squared. And we want to count these numbers, the set of these numbers. And the Landau-Ramanujan constant gives you an estimate for this number. When n tends to infinity, it is equivalent to a certain constant, which is the Landau-Ramanujan constant, times n divided by the square root of log n. So this constant has a precise definition in terms of Eulerian product. And so this constant C is 1 over square root of 2 times the product for P congruent to 3 modulo 4 of 1 minus 1 over P square with the exponent minus 1/2. So it's 1 divided by the square root of this number. You find in the online encyclopedia of integer sequences the precise value of this constant with many digits, but as I mentioned before, it starts with 0.764223. inductive way of defining the cyclotomic polynomial, and very often it is the best way to compute them. And so this form phi x square plus y square is just the homogeneous form of phi 4. So we define phi n of xy as p divided by phi of n, phi n of t. No, it's x, y to the phi of n, phi n of x over y. And this is because the cyclotomic has a degree phi of n, where the small phi is the Euler function, totally function. So the form x square plus y square is just phi 4 of xy. Correspond to the irreducible polynomial of I, and the phi 6 of y is x squared plus xy plus y squared. So because of this, the constant which occurs, which is the Landau-Ramanujan constant, I will note it by C phi 4, and so this is C phi 4. And one of the first things that we did with Etienne Couvry and Claude Levesque was to investigate the same problem for phi 6. This is not really new. We find it in the literature, but not so precisely. And the result is that we have the same evaluation with the polynomial phi 6, and we have another constant C phi 6. And C phi 6 is again given by the Euler product, which is 1 over square root of 2, fourth root of 3, and then we have the product for the p congruent to 2 modulus 3 of 1, so the same product, 1 over 1 minus 1 over p squared to the minus 1/2. So the product is the same, but the primes are not the same. When I reported on this question and this work in 2018, I mentioned the fact that we know C phi 4 with many decimal digits in the online encyclopedia of integer sequencing, but for the constant C phi 3, we were able to compute just 2 or 3 digits, and we did not know how to compute more. And Bill Allombert was listening to this talk, and after my lecture, he gave us many digits. I don't remember how many, but on the online encyclopedia of integer sequences now, you can find a very long sequence of digits, and it starts with 0.638 and 909, and so on. So this is one question which I asked to Bill Allombert, how to compute the constant C phi 6. But I asked him another question, which was to investigate the integers m, which are represented both by x squared plus y squared and by x squared plus xy plus y squared. Of course, with different I think I took the integers which are represented by some form phi n.
Okay.
So the result is that this is equivalent to a constant which is times n divided by square root of log n.
So Michel, you have also taken n greater than equal to 3. So you want to say there exists n greater than equal to 3 here is
This n here, which is greater than equal to 3.
You have greater than 0 and greater than 3. You have n greater than 0 and n greater than equal to 3.
Oh, yes. Yes, in fact, I started by saying that, and then I said we need something, and so I should write like this. This is better, thank you. And so we have a constant C, and what is the constant C? It's not really a surprise. C is C phi 4 plus C phi 6. Which means that if you have an integer which is represented by some binary form, cyclotomic binary form, then most often it will be either the sum of two squares or represented by the other form which is here. The precise result that we have is more precise. What we have is that we have an expansion. The first term is n divided by square root of log n. The next term is n divided by log n to the 3/4, and the constant which comes into the picture is the constant which occurs in the number of integers which are represented by the two forms. And then the next term is for the integers which are represented by some cyclotomic form of degree which is higher than 2. The two forms pi 4 and pi 6 degree 2, well, phi 4 and phi 3 as degree 2, and all the other forms have degree at least 4 because the degree is even, apart from phi 6. But the integers which are represented by phi 3 and phi 6 are the same. Phi 6 is just to put minus instead of plus. So this is just to say that we have to look at the forms, but not take two forms which are isomorphic, because otherwise we count twice the elements. Okay, so this was the first talk 4 years ago. In the next one, it was a joint work with Etienne Fauvry only. And what we did is the following. When we compute this, the forms of degree 2 hide what happens for the other forms. So it is natural to ask what will happen if we an integer d, and we ask that n is greater than or equal to d. For d equal to, this is what we did before. Okay, so it's n greater than or equal to 3, but here we ask the condition phi of n greater than or equal to d. We ask that the degree of the cyclotomic form is at least d. And so for d equal to, this is what we did. But we would like to know what happens if d is greater than or equal to 3 or to 4, the same. I will put 3 because when we deal with cyclotomic, with forms which are not cyclotomic, the degree could be odd. For cyclotomic form, the degree is even. So it is not n divided by the square root of log n, which occurs in this case. But the result is that we have a constant c times n divided by 2, well, it is n to the power 2 of d. So there is no logarithm in this case, and the situation is quite different if we take forms of degree at least 3. The between that, the difference between forms of degree 2 and forms of degree at least 3 is that the quadratic forms, degree 2, have a lot of automorphism, and the forms of higher degree, at least 3, have a group of automorphism which is finite. So we have the exponent 2 of d, which is not the right one in the case d equal 2. We have to divide by the square.